Hello, everybody. I will start my today another live coding session. So today I will solve this question again. Burst balloons. So yesterday I solved this question with top-down dynamic programming, and I ended up with time limit exceeded. Yeah. So today I will try to optimize this. So yep. That being said, let me get started. Firstly, let me quickly wrap. Yeah. Read the question statement again. So in this question, I'm giving n balloons indexed from 0 to n minus 1. Each balloon is painted with a number on it, represented by an array nums. You were asked to burst all the balloons. If you burst the ith balloon, you will get nums I minus 1 times nums I plus 1 coins. So the number as the number of the bursted balloon times left adjacent number times right adjacent number. That number of coins I can get when I burst ice balloon. And if I minus 1 or I plus 1 goes out of the bounds of the array, then treat it as if there is a balloon with a 1 painted on it. Yeah. That being said, return the maximum coins I can get by bursting the balloons wisely. So I will try to think of every possible, every permutation of the numbers to be bursted. Then I return the maximum coins in any of the permutation. Okay, so yesterday I solved this question with top-down dynamic programming, and the implementation is like this. So this is the recursive function, and the argument is nums. This nums is the tuple of numbers remaining. So firstly, for example, I start with this, the nums argument versus a parameter. Sorry, argument is 3158, and then, for example, if I take number 1 in line 79, the remaining numbers are 358. So nums is again called, max coins are called again with 358. Then if I choose number 5 in line 79, in the next recursive function call, nums argument is 38 in that way. And in this implementation, the time complexity was 2 to the power of n times n, because top-down DP time complexity can be calculated in this way. Yep. And the number state of the arcs is 2 to the power of n, because this nums state can be any subsequence of the original num array. So there should be 2 to the power of n variation of the argument. And for this one, time of each recursive function call, this is O of n, because in line 80, I did a for loop to decide the balloon to be bursted. And aside from that, yep, I calculate the coin I can get from bursting this one. And then I do the recursive function call with remaining nums. And in this formula, I don't have to include, or I should say, I must not include the recursive function call in the, I should exclude the another recursive function call. So I don't include, say, line 86, max coins. Yeah. So that being said, the time complexity of each recursive function call is O of n. So in total, it should take O of 2 to n times n. So that was the time complexity. So today, I will try to optimize this. Okay. So I will think with this example. Yep. Okay, so in this case, my in my last implementation, I decided which one I should choose first. Then I did the recursive function call with remaining 3, 5, 8. But to optimize this top-down DP, I will think of it backward. So I will think of it. So I will think of it as reverse chronologically. Yeah. Yeah. So I mean, what I'm going to say is past to future order. Yeah. So instead of thinking which number I should choose first, versus I should burst first, I would think which number is bursted last, finally. Yeah. So I was thinking in that way. If I think, if that, I will think of the case if in which this number 2 is bursted in the end. In that case, I can calculate how many number of coins I can get from this 2. It is 1 times 2 times 1, which is 2. Because 3 has been bursted any already, and 5 and 8, they have been bursted already. Because 2 is the last one. Yeah. So I get 2 coins from here. And when I think of other coins, what I want to get is number of coins I can get from this range, which is 3 only. And also, I want to calculate total number of max coins I can get from this range, 5 and 8. So once I calculate each of them, the total number of coins I can get from the whole range, 3, 2, 5, 8, is this one plus 2 plus this one. So that's how it works. And when I think of this 3, how many coins can I get from this 3? So when I burst this coin, I can say this 2 is still remaining because I thought of the case when 2 is the last balloon to be bursted. So 2 is still remaining. So the right number of 3 is now 2. And how was the left number? It is 1. Because there isn't any number remaining here, or I should say it actually never exists. There is no number on the left side of 3, so I will think of 1 instead, as written here. If it goes out of the bounds of the array, then treat it as if there is a balloon with the 1 painted on it. Yeah, I will think of 1 here as a fallback. So I can think that this should be 1 times 3 times 2 is 6 coins from this range. Good. And how about this range, 5 and 8? I can think of it in the same way. So let's say I take 5. If I take 5, which means that 5 is the second to last balloon to be bursted in this range, 2 or later. It doesn't matter in which order the right hand side range, balloons in the left hand side balloons are bursted. It doesn't matter because there is 2 which is remaining, and this blocks left hand side balloons. So when I think of this range, I don't have to take care of left range, left hand side of 2. Yeah. So when I take a look at this, So this is the, let's just say, if I take 5 as the second to last balloon, how much point can I get from here? So I can earn 2 times 5 times 1 is 10 coins, because 2 is still remaining, because um 2 is the last balloon to be bursted, and here 8 is deleted later than, sorry, I mean before 8, because it hasn't been deleted yet. So this 8 doesn't exist anymore, so I fall back to 1. Yeah, so that's why I get 2 times 5 times 1 is 10. Okay, so that being said, seems like I can use the kind of range TP. So the recursive function interface should look like this. So I will try to guess the max total number of coins in the range low to high. I mean, by bursting all the balloons in this range. But there is one thing I had to take care when I think of this. Let's say I have range 5 and 8. Or maybe I can make it more clear with this. So when I take this or this or this as the last index, I can easily calculate the number of balloons, the number of coins I can get from here. Because, no, sorry, is there something wrong? It's not easy. I have to be thorough. Or I should say, I should be careful. Because this is the last index, which means that this doesn't exist anymore. This doesn't exist anymore. This doesn't exist anymore. This doesn't exist anymore. So I'm interested in this number or this number. So I can say this is left. Sorry. So the index one I'm interested in is index which is left hand side of the current range and not included in the current range, and not bursted and closest to the current range. Yeah. So with that index and with that number of the balloon as that index, I can calculate how many coins I can get from by, say, choosing the last balloon as this one. Also, I want this one here, which is the index of the balloon which has not been bursted yet, which means that it should be bursted later. Yeah, and on the right hand side of the current range and closest to the current range. Yeah. And this number is also, I mean, this index is also important because when I choose the last index in the given range, current range, this should be the right adjacent balloon of the chosen last balloon, no matter which I choose. Yeah. So that being said, this is called high index and this is now called low index. So let's call this one left hand side remaining index. Yep. And let's call it right hand side remaining index. Okay. So these are important when I think of the max total number of coins in the given range. So I need them as the argument. Okay, so with that being given, I can calculate the number of coins I can get from this range because I will think of the last index in this range. And I will calculate the number of coins I can get from here. As I said, it should be this times last index number times this number. Yeah. I will quickly write it. This. And also I can calculate the right coins, the left coins. I mean, if I choose this as the last index, I want the total number of coins in this range. So I can calculate it recursively. And also I can calculate right coins. Then I get total coins by getting the sums. Then I will return the global max of total coins in the end. Yeah. So this is basically what I would do in the recursive function call. And for the base case, I can simply say if low is higher than high, low is larger than high, this means that there is not any balloon in the given range low to high. So in this case, I return 0. So this is the base case. Okay, so this is the basic idea. So let me implement the code. Even though I've almost implemented the code in a bit sloppy manner. Okay. So firstly, I will use this as the recursive function method. And in the end, I will return max total coins in the given range. I mean, in the whole range. And the rest remaining index by the remaining index. So this can be the problem because this should be, I would say this should be -1 and length of nums which are out of the index. So even though it is possible that I pass the -1 and length of nums here and here and handle them in a different manner in this recursive function. But I will use a technique that I put 1 as the suffix and prefix of the given array nums. And now the given array looks like this. But what I'm interested in is this range, 1 and 1, there's no balloon. But I just put it as the left remaining index or right remaining index. So the range would be 1 to length nums minus 2. And 0 and length nums. Sorry, self.num. Yep. So in this way, left remaining index is here and right remaining index is here. And the range to be specified is this range. Yeah, this is totally, yeah, this totally makes sense. And I will quickly say Why I can choose this index 0 as left remaining index first? Because if I choose this as the last index, I would try to I can calculate the total number of coins, number of coins I can get by bursting this number 2 by 1 times 2 times 1. Again, it is because 3 and 2 or 8 will be deleted in the future. No, sorry, deleted in the past. So it doesn't exist anymore. So left adjacent and right adjacent numbers of 5 is 1 and 1. And when I choose this as the left rem index and this as the right rem index, it totally makes sense. Yeah, it as expected. So it's okay. Okay, that being said, I implement the max total coins method. So for base case, this. And then I will choose the Rust index. So this is the Rust index, and I can calculate the Rust coins with okay. Now I get the coin I can get from the chosen Rust index. The remaining number of coins are here and here. So far, I think this makes sense. And left remaining index doesn't change. Yeah, because there's no change on the left hand side segment. But for the right remaining index, maybe there's a change. So I will take a look. So if this is chosen, the remaining range is this on the left hand side. So I'm interested in the number, or I should say index, which is right hand side of this range and not bursted yet and closest to this range. Obviously, this is the last index I chose because I chose this previously, which means that chronologically, this will be deleted later, which means that this is not bursted yet. And obviously, this is on the left hand side and closest to this range. Yeah. So this last index is exactly the right remaining index in the Corey function. Yep. And when I think of the right coins, the similar thing happens. Oh. Like this. So I will quickly say, when I think of this range, the index of the balloon, which is still remaining, and left hand side of this range, and closest to this range is obviously this last index I chose. The last should be specified. And for right remaining index, there's no change because right range, on the right hand side, there's no change. So in this way, I can calculate last coins, left coins, and right coins. And I can calculate the total coins. Okay. And I will update the returned coins. So global max total. Then I return global max total in the end. Okay, this is it. Let me work through my code with a small example. Maybe I don't completely work through until the end, but I think taking a look at a few, recursive function codes will even makes our understanding more clear. So I will take a look. So let's think, given nums is 3, 2, 5, 8. In that case, self.nums becomes like this. Yep. Then in line 113, so low is 1 and high is, because there's 6 element, high is 4 and left rem index is 0, right rem index is, this should be -1 because this should be the last index. This should be 5. So now it works like this. Left remaining is here, low is here, and high is here, and this is right remaining index. Good. And in right 119, low is not larger than high, so I go to right 122, and minus infinity is now global max total, and I iterate the last index. So I start from this index 1. So when last index is 1, last coin I can get is self.num left remaining index, which is 1. Self.nums last, which is 3. Self.nums right remaining index, which is 1. So in total, it should be 3. Yes, this is good. For left coins, I call the recursive function. But here, the first two arguments, low and high, should be 3, and 3 minus 1 is 2. So 3, 2, in this case, obviously this is edge case in line 120. So this should be 0. For right coins, it calls the method with last index plus 1, which is 2, high index, which is 4, and last, which is index 1, and right remaining index, which is 5. So what happens is that low high range is this, and left remaining index is 1, which is here, and right remaining index is here, this. Yep, and this is completely as expected because I'm interested in this range, and the raining balloon, which is on the left hand side and not bursted and closest to the given range, current range, is this one. Yes. And same for right remaining index. This is correct. Okay, so that being said, seems like so far everything is correct. I don't go into the another recursive function call, this one, to save my time. But so far I'm confident. And let's assume these are correct. I will just quickly review my code, remaining code. Yeah. So in 137, total coins is the sum of all the last coins and left coins and right coin. Yep. And global max total should be the maximum of the total coins. So it's good. Yep. And I written the global max total. Good. Okay. So even though I couldn't dry run my code until the end, but I covered almost all the lines and I'm pretty confident. And the logic looked like, yeah, as expected. So I execute my code. Good, accepted. Okay. So that being said, I will do the complexity analysis. So currently, when I take a look at the argument, there is low, high, left rem index, right rem index. So it seems like there are n to 4 variations of argument, but actually not. So let me tell you why. So firstly, let's see what are given as the argument. And let me tweak something a little bit. This is another recursive function call. This, yep, so I will print it out. So what I notice here is that left remaining index is next to low index. It's always true. 1, 2, 2, 3, 3, 4. And high index and right remaining index, they're adjacent. 4 and 5, 0 and 1, or 1 or 2. Yeah. So seems like they're adjacent. And this is true because let's remember the process I did. Given the current range, low to high, yep, I chose some number as the low index, sorry, last index. Yep. So when I choose the last index somehow, somewhere, this splits the current remaining range in this way. And as I've seen, this last is given as the right remaining index. Yeah. Or maybe I can just take a look at this. Yeah. So when I choose left coins, which means that on this side, this left segment is splitted. And when I take a look at high here and right rem index, which is the first argument, it is last minus 1 and last. So I can say, let me clean up. Here, right remaining index is equal to high plus 1. And here, right coins. So when I take a look at this first argument and third argument, I can say left remaining index plus 1 is low. So what I can say is when I split it here, then on the left hand side, this one, the high, which is set new, plus 1 is right remaining index. Yeah. So because first three, this range satisfies low is LR plus 1, RR is low high plus 1. And once this is met, as long as I split and set high plus 1 is RR or LR plus 1 is L low, it is always met. The high plus 1 is right rem index is always met, and left rem index plus 1 is low is always met because I split the segment as such. Yep. So that being said, when I think of the high index and right rem index, I mean, this one and this one is always adjacent. And this one and this one is again always adjacent. So theoretically, I have to choose n squared pairs. Deciding low and high, always left rem index and right rem index is decided, which means that there are n squared variation for the argument. So when I look back to this, this should be now n squared, and this should be O of n, because when I took a look at this function, what I do is in line 145, there is a loop, for loop of n steps at max. And aside from that, all the operations are constant. So it should be O of n time complexity, excluding another recursive function call. So it should be the time complexity should be O of n cubed. And for space complexity, firstly, I use the self.nums array, which is ranks n plus 2. And also, I use the recursive function call. So basically, low and high, which are the argument, basically. And firstly, it begins with the first index until the last index. And in the worst case, let's say I would always choose the last index and continue the recursion. In that case, length of the current range is decremented by 1 always. So the depth of the recursive function, which is exactly how many steps do I need until the current range becomes 1, is n minus 1. So it should be O of n. O of n, I mean, the best recursive function call stack is O of n. So there is a space complexity as the recursion stack. So it should be O of n. So in total, it is O of n. Yeah, so this is the extra space complexity. Good. Okay, that being said, I could optimize quite much from 2 to n times n to n cubed. Yep, great optimization. Okay, so that being said, I quickly wrap up my today's coding practice. So today I solved the question burst balloons again, and I optimized the yesterday's solution. So yesterday I solved this question with top-down DP, and the point was that the argument of recursive function here, nums, is the remaining numbers in the original array nums. So the variation of the argument was 2 to the power of n, which is exactly the number of subsequences of the given array. But it caused too much time complexity. So today, I optimized it. I thought of it, reversed chronologically. So I thought of it from past to future. No, future to past. No, future to past. Or I should say, last one to first one. Last birthday to first birthday order. So I sorted backward. And what happens was that I could make it range TP, which means that I just have to take care of the current range. The range which current recursive function is responsible for. So in that way, I could optimize the time complexity to n cubed because number of variations of the argument is now n squared. So yeah, that's how I optimize the dynamic programming in my today's video. Okay, that being said, I finished my today's coding practice. Thank you so much. Bye.